Good evening and welcome to Advanced Electrical Networks. This is lecture 47. So far in this course we have seen how to analyze LPTV systems. We found how to analyze systems where the output of the LPTV system is sampled and the sampling rate happens to be the same as the rate at which the system is varying. We also saw the corollary last time, where we showed that if you drive an LPTV system with a modulated sequence, you can think of the output as being the result of driving the same modulated sequence through a linear time invariant filter. Today we will discuss noise in LPTV circuits. So, and the premise is the same. So, we have an LPTV system N, which is LPTV at Fs, and most of the time we are dealing with noise sources, which are device noise sources, right. And these noise sources can be modeled by some noise spectral density. If this is a resistor, for example, the two-sided spectral density is 2 kTr volt square per hertz. If it's transistor noise, it's 2 kT times 2 kT times GM times some correction factor, 2/3 typically, or maybe more depending on the device construction. So, the bottom line is that you can think of device noise as being some spectral density that is known from the physics of either the device or the component. And in this case I am just assuming that this is an input noise voltage, and the output of the system is some V out. And just like how we did with the time invariant case, we also can do this with the time varying case, and the idea is the following. So, if you draw the block diagram, you have Vn, and then it is going through H0 of J2 pi f, H sub k of J2 pi f, and this gets multiplied by e to the J2 pi kfs times t. This is H sub minus k of J2 pi f. This is e to the minus J2 pi kfs times t. We add all these things up. This is V out. Correct. The question is, what is the noise power at a frequency f here. So, we are interested in S V out of, right. So, in other words, what we are interested in is the following: we basically take V out, correct, pass it through a narrow band filter centered at some frequency f, right, and we measure the mean square value all right. And the difference between the two differences between what happens in a time invariant circuit and a time variant circuit, right. In a time invariant circuit, well, if you have an output noise component at a frequency f, that can only come from an input frequency, a noise frequency which is at f, right. Now, we have to worry about not merely an input noise at or the power of the input noise at f. Very good. So, you also have to worry about noise at multiples of f plus minus k times fs, right. And the other thing is, now because you have to worry about noise at multiple input frequencies, we obviously have to worry about the transfer functions from those frequencies to the output. So, that is one aspect. The other thing is that when we are talking about a time invariant network, the noise at the output of an LTI system driven, see, if you look at Vn, right, it turns out that device noise or resistor noise, for instance, if you look at the power in a narrow frequency band, whether you measure it now or whether measure it a time t later, it turns out that the properties, the statistical properties of the noise do not change, right. So, such a noise is called stationary, right. Now, if you take a stationary random process and process it through a linear time invariant system, well, the gain of the time invariant system does not change with time. So, the output noise is also stationary, that basically means its properties do not change with time. So, if V of n is stationary, if you look at this block diagram, then clearly all the noise at all these points is all stationary. However, when you take this noise and multiply it by a sine wave, right, okay, then the noise no longer becomes stationary. It only becomes, I mean, because at some point in time, let us say the cosine is 0, right. Then how much ever noise you have at the input, the output is 0. So, in other words, the mean and the variance and other statistical properties of the noise, right, will depend on time, right, because you are multiplying it by you are taking a sequence, I mean a noise process which is stationary, it is not varying with time, and you are passing it through an amplifier or a gain which is changing with time. So, it is only natural that the output also has statistical properties that change with time, right. So, and it turns out and because our gain is varying periodically, the statistical properties of the noise of the output also change periodically, and such processes, random processes, are called cyclostationary. Nice. Okay. All right. But it so turns out that most of the time when you are making measurements, you are looking for power in a very narrow band, right. So, you take this process which is varying rapidly with time and you pass it through a narrow band filter, and what is the job of a narrow band filter? A narrow band filter just simply averages out the variations, and you will get something which is constant, right. So, what you measure, the mean square value that you measure at the output is an average of what happens throughout the complete cycle, right. And as you can imagine, the process of noise computation is in a LPTV network is a lot more involved than the LTI case, simply because even if you had only one source, you have to worry about the strengths of the noise at all f plus k fs, as well as the transfer functions from those from those frequencies to the output at f. So, the question is, what all frequencies can alias? In other words, So, what all frequencies can fold to a certain frequency f at the output of the LPTV system. So, to do that, what would you do? Yeah, we can use if you know it off the top of your head, that's good. Otherwise, we can use the concept of interreciprocity, and so if we did that, well, what would we need to do? We will turn the signal flow graph the other way around. The summing node becomes the pick off point. So, and you have to, the gain has to become at reverse time, and you excite it with e to the j 2 pi f t, right, and this becomes a summing. Right, and what do you expect to see here? So, e to the j 2 pi f t here becomes e to the j 2 pi f plus k f s times t, all right, and what you get here is h sub minus k of j 2 pi f plus k f s times e to the j 2 pi f plus k f s times t, and now we have to sum over all k's, right. So, basically what this is telling us is that if you excite, if we excite the original LPTV system at a frequency f plus k times f s, what will happen? The output will consist of a frequency f, right, and gain of this path is h sub minus k of j 2 pi f plus k f s, right. Intuitively this seems this is very convincing, right. If you put f plus k f s, you go the output has to be at f. So, you have to put in an input frequency which is f plus k f s and go through k down conversions to get to the output. So, this is now the gain from an input at f plus k f s to. So, let us say the noise spectral density S V in of f is known. So, this is the input noise spectral density, right. what comment can we make about the output? I mean, what so if we want to find the total noise power at f at the output, what do we think we should do? Well, let's take a look at this. So let's say so assume this is symmetric. Okay. So this is the output frequency. So this is, let's assume, so this is SVN of f, all right, and this is SVO of V out of f, correct. So this is f. So we have, so what is the transfer function from there to there? H0 of J2 pi f, right. But it is not just this tone that will fold, you will have f plus fs, right, blah blah blah, in general f plus kfs, okay, and this will fold over with a gain h sub minus 1 of J2 pi f plus fs, and this will fold over with a gain of h sub minus k of J2 pi f plus kfs. So what comment can we make about the output power spectrum? If you put a narrowband filter at f and measure the average power that is coming out, what you would expect to see is SV out of f, which is sum over all k h mod h sub k, h sub minus k of J2 pi f plus kfs mod square times SVN of f plus kfs, all right. And therefore, even for one calculation, I mean for one input noise source, you can see that this is a very messy affair, right. Fortunately, there are simulators that okay, will do the calculation for you, right. Okay. And a big part of the calculation is finding all these h sub minus k's of all this stuff, and that is easily done using the adjoint network. Now, so what do you call messy to compute? And therefore, usually you resort, I mean hand calculations, you forget about it and do it with a computer using adjoint techniques, okay, to find all these transfer functions.